I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to do the discussion on definitions and terminology. So what is the importance of definitions and terminology? We are going to discuss first, and then we'll go to discuss these definitions in each module one by one. Now, where do you find this document on definitions and terminology? If you go to our IARE website, in our learning and management system, you will find the stack of course resources. That is all material related to the course. We are discussing about the course engineering physics. So you will find the course description. You will also find the other documents, the definition and terminology, question bank, and all these documents are uploaded. So you can see the document in your learning management system. And we are going to discuss on definitions and terminology. So first let us understand what a definition is. What is a definition? The act of defining or of making something definite, distinct and clear. So that is the meaning of definition. Or if you put it in other words, definition is a formal statement of the meaning or significance of a word or a phrase or an idiom, as you usually find it in dictionaries. Or it can also be expressed as the essential nature of something, a statement which expresses the essential nature of something, we call it as definitions. And why is a definition so important? Because definitions enable us to have a common understanding of a word or a subject. Common understanding here means whatever I define, it has got a specific meaning, and even when you are using it, you are also using it in the same sense. So it will give us a common understanding of the subject. And they allow all of us to be on the same page when discussing or reading about a issue. So suppose I'm talking about distance. Distance is given by the change in position. So even for you, it will be the change in position. Even when I measure, it is the change in position. So there is no ambiguity in that if we are using the definition as it is. Therefore, we need to make sure that we properly define our words and phrases so that all will understand and understand very clearly. Then what is terminology? The body of terms that are used in particular with technical application in a subject or a study or in any profession, we call it as terminology. Then what is the importance of terminology? Terminology plays a very important role in understanding the context and specialized texts. Understanding the intricate terminological details of the technical and scientific context helps students to comprehend what the main message of the document is. So when you try to understand the terminology, and when you get the terminology right, you will understand what the text says. And it helps specialists to transmit the content more effectively. So if somebody is doing document writing, so whatever terminologies that they are using it to transmit the information or transmit the content. So it helps the specialists also to transmit the content very effectively. So whenever we are talking about something in scientific reasons, so it is very important to use the right definitions and use the correct terminology. So now let us go on to discuss these definitions and terminology module wise. So today we are going to discuss in the first module. So in the first module, what are the topics we have? We are going to see about the introduction to quantum mechanics. Then we'll see de-Broglie hypothesis. Then wave particle duality, Davisson and Germer experiment, Schrodinger wave equation, then a physical significance of the wave function, and particle in one dimension box. These are the topics we have, and we are going to discuss all the terms and the definitions that are related to these topics one by one. So first is, what is quantum mechanics? What is quantum mechanics? It is a branch of physics which deals with the behavior of matter and light on atomic and subatomic scale. So if you speak about physics, physics is all about the study of matter and the interaction of matter with its surroundings. Now, what is special about quantum mechanics? It deals with this kind of matter at atomic and subatomic scale. So when I say atomic scale, of the order of 10 to the power of minus 10 meters, so small. So when we are dealing with small particles, we talk in terms of quantum mechanics. Then what is classical mechanics? It is a branch of physics that is based on Newton's laws of motion, that is applicable to systems that are very large. So whenever you are talking about systems that are large when I say here, maybe from the size of a billiard ball to the size of a rocket. Any size you take which is measurable, which is macroscopic, all the Newton's laws of motion apply. So whenever we are talking about such kind of bodies, we use classical mechanics. Now to understand the whole picture very clearly, so we'll see the development of theories. We have defined two theories, the classical mechanics and the quantum mechanics. So how it is going to apply? Now first, the classical mechanics, also called as Newtonian physics, which is used for macroscopic bodies. So Newtonian or the classical physics is used for macroscopic bodies when the objects are bigger in size. But when things get small of the atomic scale, we are using quantum physics. So this is what we have discussed now. But when things get fast, we use special theory of relativity. And when things are small and fast, they're small and they're fast, they're moving fast, then we use the quantum field theory. So this gives the clear picture of how we are classifying different theories. Now coming to black body. What is a black body? So what is a black body? Here we see in the figure, it is a hollow sphere with a small hole drilled onto it, and the inner surface of it is coated black. So whatever light that is incident, radiation that is incident, suffers multiple reflections inside. At each point, a part of the energy is absorbed and a part of it is reflected. So here, out of the reflected part, a part of it is absorbed and reflected. So what happens here is, after multiple reflections, it completely absorbs all the radiant energy. And literally, there is no reflection outside. And if you see this black body, it absorbs the all energies when it is at a lower temperature compared to the surroundings. But when it is at a higher temperature, it will emit all radiations at all frequencies. So it radiates all frequencies with a spectral energy distribution. So let us see the spectral energy distribution, how it is. So when we draw or plot a graph for wavelength versus intensity at different temperatures, see here it is 3000 Kelvin, 4000, 5000, 6000 and so on. So what we see here is, as the wavelength varies, the intensity also varies. So here this is for the temperature 3000 Kelvin, and for temperature 4000, this is the graph. So on we get, and this is the visible range. So what we are seeing here is how the spectral radiation is distributed. Next is, what is photoelectric effect? A phenomenon in which electrons are emitted from the surface of a metal when light of suitable frequency is incident on it. The electrons that are ejected are called photoelectrons. So let us see this phenomenon. So you consider a surface. This is a metal surface. Now light is incident on this surface. This is the light. So when light of suitable frequency, this is very important. When it is incident on it, electrons are emitted. These are the photoelectrons that are emitted. So what is suitable here? So when you see a metal surface, these electrons are bound to the nucleus with certain energy. So if we have to detach these electrons, we need to supply an energy which is at least minimum equal to the energy with which it is bound to the nucleus. So if the energy we are supplying is less than that, see, these electrons cannot be detached. So for example, I say these electrons are attached to the nucleus with energy of say 5 electron volt. So the minimum energy that we have to supply to remove the electron is 5 electron volt. Otherwise we cannot remove. So the energy when we are supplying is suitable. It is above that. Then the electrons are emitted from the metal surface, and this phenomenon of emission of electrons from a metal surface when light of suitable frequency is incident on it, we call it as photoelectric effect. Then what is de-Broglie wavelength? So the wavelength that is associated with an object in relation to its momentum and mass is known as de-Broglie wavelength. So it is the wavelength, no doubt, but it is named after the scientist de-Broglie. So at this juncture, it is very important to understand or to know about this scientist de-Broglie, after whom this wavelength is named as de-Broglie wavelength. So who is de-Broglie? In the year 1924, Louis de-Broglie made a very bold suggestion. What was his suggestion? If radiation, which is basically a wave, can exhibit nature, particle nature under certain circumstances, and since nature likes symmetry, then entities which exhibit particle nature also should exhibit wave nature under certain suitable circumstances. So this is the suggestion that was given by de-Broglie. What he says is, when we are talking about light, which is actually a radiation which has got wave nature, under certain circumstances we are considering them as particles. This is after the Einstein's photoelectric effect. Then he said, he thought very logically, and he said, because nature likes symmetry, particles also should exhibit wave nature. When wave nature can exhibit particle nature, particles also should exhibit wave nature. Then he has to explain his concept. So in order to explain his concept, he used this de-Broglie wavelength. So that is named after him as de-Broglie wavelength. Now the next one is momentum. Define momentum. Momentum is the product of mass and velocity. So generally we denote the momentum by P. P is equal to M into V. It is a vector quantity. Vector means what? It has both magnitude and direction. And the SI unit, if you have to write for momentum, the SI unit will be kilogram meter per second. Mass is measured in kilogram. The velocity is measured in meter per second. Now, Newton's second law of motion states that the rate of change of momentum is equal to the force that is acting on the particle. So this is the famous Newton's second law. So the rate of change of momentum, that is dp by dt, is equal to the force. So this has given rise to our very famous equation F is equal to ma. So we are getting this relation F is equal to ma from this Newton's second law, F is equal to dp by dt. What is p here? Momentum we have seen. So we can write it as d by dt of mv, or we can write it as m constant into dv by dt. And dv by dt, the rate of change of velocity, is nothing but acceleration. So we write it as ma. So this is a very fundamental equation in Newton's laws of motion. Now coming to the Einstein theory. So state how Einstein's theory of relativity gives energy in terms of mass of the body. So what is Einstein's relation? E is equal to mc square. So this relation expresses the fact that mass and energy are the same physical entity, and they can be changed from one to the other. So what is the example we can see here? Speed of light is a large number and the square of it will be very large. A small amount of matter can be converted into tremendous amount of energy. So when we are talking about E is equal to mc square, even if mass is small, the velocity of light is very big. C is equal to 3 into 10 power 8 meter per second approximately. So C square will be even large, 9 into 10 power 16 meter per second. So whenever there is a small mass that is getting converted into energy, it will be very huge. The energy will be mass multiplied by C square. So this is the key in the nuclear power reactors. So this is the key to the power of nuclear reactors, when a small amount of mass disappears. So an equivalent or the energy is very huge. Now give Planck's Einstein's relation of energy E and frequency nu. So Einstein defined a quantized unit or a quantum of electromagnetic energy, which is called as photon. So the energy of this photon is proportional to the frequency of the radiation. So the energy always depends upon the frequency. So E is proportional to nu. If nu is the frequency of the radiation, the energy is proportional to frequency. So we can remove the proportionality sign and put a constant, and that constant is h. So this gives us the relation between energy and the frequency. So E is equal to h nu. E is the energy of the photon of frequency nu, and h here is the Planck's constant. This is given by the scientist Planck. So it is named after the scientist Planck as Planck's constant. Next is define wave vector k. So what is a wave vector? A vector indicating the direction of wave propagation and the phase delay per unit length. So wave vector always denotes the direction of propagation, and also it denotes the phase delay per unit length. And it is always perpendicular to the wavefront. And the magnitude is the wave number, which is given by k is equal to 2 pi by lambda, where lambda is the wavelength. Always we use this formula in our expressions. We have used k is equal to 2 pi by lambda. This is the wave vector where lambda is the wavelength. What is h? We have already discussed. H is the Planck's constant, named after the scientist Planck, who gave us the relationship between energy and frequency. This is the energy of the photon, and this is a constant, he said. He repeated the experiments with the different frequencies and calculated the energies, and there is a constant on which it depends, which he gave the name as Planck's constant, named after him as Planck's constant. And what is its value? Its value is 6.63 into 10 power minus 34. It is approximated. In some books, it will be given as 6.625 into 10 power minus 34, or whatever value you can use. Both are correct. They are approximated values. What is h bar or h cross? You call it as h cross or h bar. This is nothing but a modified form of Planck's constant. So how it is modified here is, whenever you are having h divided by 2 pi in expressions where you have h divided by 2 pi. H is a constant, 2 pi is also a constant. So instead of writing 2 constant, we will write it, the value of h by 2 pi is denoted as h cross, and it is nothing but the quantization of angular momentum. So h by 2 pi gives the angular momentum. Now what is a wave function? Wave function is denoted by psi. It gives information about the quantum system, all information about the quantum system. So a quantum system can be one or many particles. Now if you talk about a system, this wave function is like an Aadhaar card. So if you have your Aadhaar card, you can get lot of information, derive information from your card. You can get the name of the person, you can get the date of birth, the address, whether male or female. All this information can be drawn from one. So if you know the wave function, you can find the position, you can find the energy, and you can also find the momentum of the particle. So we call it is a wave function that gives the information, all the information about the quantum system. Then why the de-Broglie wave associated with a moving car is not observable? So we have already discussed de-Broglie wave. What did de-Broglie say? If radiation can exhibit particle nature, particles also should exhibit wave nature. And he could prove it with the help of his de-Broglie wavelength. But now the question is, if a car is moving, then why are we not able to see the waves that are associated with it? That is the question. Why we are not able to see the waves? So here what we need to understand is lambda is equal to 1 upon m, or the wavelength is inversely proportional to the mass of the object. Now if we are talking about a car, the mass of the car is very large. So if m is large, lambda will be very small. It is inversely proportional. M is inversely proportional to lambda, that is inversely proportional to the wavelength. So when we are talking about the size of the car, it is very large. So lambda is very small. Therefore, we cannot see the waves that are associated with a moving car. Now the next one, what is rest mass of a photon? So when we are talking about a wavelength, we have talked about the Planck's law. What Planck's law says, energy is radiated in the form of wave packets, and this energy has both wave and particle nature. And these packets we are calling them as photons. And these photons are chargeless and massless particles that travel with the speed of light. So at rest, when it is at rest, the rest mass of the photon is taken to be 0. When it is at rest, its mass is 0. So they are massless particles. Now what is de-Broglie wavelength? So whenever we are talking about material particles like electrons or protons, then what will be the wavelength that will be associated with it? Because we have taken, according to de-Broglie, they should exhibit wave nature. So when they are exhibiting wave nature, for a wave, what is the wavelength? So the wavelength lambda is given by h upon p, where lambda is the wavelength and p is the momentum, h is the Planck's constant. So we can also write h upon p as h upon mv, where m is the mass and v is the velocity. So the wavelength of matter waves depends on mass as well as velocity. Now coming to the next one. Are matter waves electromagnetic waves? No, they are not. Because electromagnetic waves, if you see, they are produced by accelerated charge. But de-Broglie waves are independent of the charge of the particle. So they are not electromagnetic waves. Then what is the difference between light waves and matter waves? So the velocity of light waves in vacuum is constant. But the velocity of matter waves depends upon their wavelength. We have seen just now lambda is equal to h by p or h upon mv. So when lambda is equal to h upon mv, so I can write v is equal to h upon m lambda. So the velocity depends upon the wavelength. Now comment on the statement. Heisenberg's uncertainty principle is valid for all kinds of particles. So what do we comment on this? What Heisenberg's uncertainty principle says? We cannot find the position as well as momentum of the particle at the same time. There is certain uncertainty. So for atomic particles, there is always some uncertainty in the measurement of two conjugate quantities like position, momentum, or angular position, angular momentum, energy, time, etc. But for particles of large size, if you take the particles which are larger in size, this uncertainty is small as compared to the wavelength of, compared to the value of h. So in such cases, uncertainty is not observable. So it is not applicable in all cases. So we are talking in atomic particles, there is uncertainty. But when the size is big, this uncertainty is not observable. Now describe Compton wavelength. What is Compton wavelength? So Compton wavelength is a quantum mechanical property of the particle. So whenever we are talking about quantum mechanical, smaller in size of the atomic size. And the Compton wavelength is equal to the wavelength of the photon, whose energy is the same as the mass of that particle. Understood? Compton wavelength is equal to the wavelength of a photon. What is photon? It is massless, chargeless, whose energy is given by E is equal to h nu. And if the energy is the same as the mass of the particle, then we call it as Compton wavelength. So let us try to understand about this Compton effect. So convincing evidence of particle nature of electromagnetic radiation was given by the scientist Compton. Compton is the name of the scientist. He gave an evidence for the particle nature of electromagnetic radiation. So he was actually doing experiments or investigating on the scattering of X-rays. And what he observed is when these rays lost some energy in the scattering process, they were coming out with slightly decreased frequency. So then he tried to understand what is the reason behind this decreased frequency. So what he said is the increase in wavelength of X-rays or other electromagnetic waves that have been elastically scattered, and it is a principal way in which the radiant energy is absorbed in matter. So that is what Compton's effect says. It is the increase in wavelength of the X-rays and other electromagnetic radiations that have been elastically scattered, and it is a principal way in which radiant energy is being absorbed by the matter. So how do we understand it? When a beam of monochromatic radiation of high frequency falls on low atomic number substances like carbon or graphite, the beam gets scattered on colliding with the electron. So whenever there is a collision, see here, this is the substance. You consider there is an electron in that substance. So a photon is incident on it. So when a photon of energy E is equal to h nu is incident on it, then what happens? This photon gets scattered and it moves with a slightly decreased frequency. And the electron on which it is incident will recoil. That is why we are calling it as elastic collision. So what we understand here is the scattered photon will have a different frequency when compared to the incident photon. So what is happening? The colliding photons transfer some of their energy and momentum to the electrons, in which they, due to which they recoil. And at the instant of collision, new photons of less energy and momentum are produced, and they scatter at different angles. So we have the modified radiation, which is having lower frequency and large wavelength, and the unmodified radiation, which is having the same frequency and wavelength. So this change in wavelength is given by the Compton shift. So what we understand in Compton effect is the Compton shift. So the shift in frequencies or the change in wavelength is studied with the help of Compton effect. So the next one is define matter waves. What are matter waves? The waves associated with particles of matter. So whatever waves we are talking about, because we said particles also should exhibit wave nature. So the waves that are associated with particles means electrons, protons, etc. They are called as matter waves or de-Broglie wave, named by the same scientist who gave the first very bold suggestion he has given. So it is named after him as de-Broglie waves. So is light made up of particles or waves? Light exhibits both particle and wave nature. So we say it has got wave-particle duality, dual nature. So light exhibits dual nature, that is wave nature as well as particle nature. Now what is a system in quantum mechanics? So a quantum system is a collection of physical objects that is to be described by the wave function. So when I am calling about a system in quantum mechanics, when I say a system is under consideration, what is a system here? A quantum system is nothing but a collection of physical objects that we are describing with the help of the wave function. So what does an electromagnetic wave contain? Electromagnetic. So it consists both electric as well as magnetic fields. And these electric and magnetic fields are perpendicular to each other. So whenever we talk about electromagnetic radiation, it consists of electric and magnetic fields which are perpendicular to each other. They are perpendicular to each other. Define wavelength. What is wavelength? It is a spatial period of a periodic wave, or it is the distance over which the wave shape repeats, or it is the distance between consecutive corresponding points of the same phase. So let me explain this with the help of this diagram. So suppose I draw a wave like this. So we have seen the basic definitions for wave. This is one complete wave. So the distance over which the wave's shape repeats. So after this, the shape repeats again. So this is called one wavelength. Or it is the distance between corresponding points of the same phase. Means if you see the point here, the phase of vibration is this, or the state of vibration. So when you come back again here, again the particle is having the same state of vibration. So the distance between these 2 points which have the same state of vibration or the same phase, we call it as wavelength lambda. Now how is wavelength related to the mass of the particle according to de-Broglie? So lighter the particle, greater the wavelength. We have the relation lambda is equal to h upon mv. So lighter the particle means if m is less, lambda is more. It is inversely proportional. Lambda is inversely proportional to m. So lighter the particle means the mass is less. So greater the wavelength means the wavelength is more. That is how we understand about the wavelength. Now state Bragg's law. Bragg is again the name of a scientist who studied the crystalline studies, and he gave us a famous relation, that is 2d sine theta is equal to n lambda. This is the famous Bragg's law. So what we see here is when monochromatic X-rays are incident upon a crystal, atoms in different layers acts as source of scattering radiation of the same wavelength, and the intensity of the reflected beam will be maximum at a certain incident angle. When the path difference between the two reflected waves from the two different planes is an integral multiple of the wavelength. So this is the integral multiple of wavelength. So what he is telling here, the intensity is maximum at certain angle where the path difference is the integral multiple of the wavelength. So whenever we are talking about the path difference 2d sine theta, if it is equal to n lambda, then we are saying that the intensity is maximum at that certain incident angle. Now what is a wave particle duality? Duality means, dual means two. So what is this dual nature? An idea that light and subatomic particles. Subatomic particles means like electrons and protons we are talking about. They can behave as waves and also as particles. That is dual. So what is this dual nature? Radiation is supplemented with particle characteristics. So to explain certain phenomena like photoelectric effect, when we were talking about photoelectric effect, we considered light as particle. Actually, radiation is wave nature. So we are telling that it has got both wave nature as well as particle nature. And in similar lines, material particles have to be supplemented with wave aspect for a full understanding of their behavior. So how the particle moves. So then we are talking about the wave aspect. So this is what we call it as dual nature or duality. Now what is the principle used in Davisson and Germer experiment? So in Davisson and Germer experiment, what we see here is a beam of electrons that are emitted from an electron gun. We have an electron gun. This filament, when it is heated with the help of this supply, when it is heated, the electrons that are emitted are striking a nickel target. So beam of electron is allowed to fall on the nickel crystal. Now the atoms you see here, which are represented by the small circles, they cause diffraction of the electron beam at different angles. This is the angle at which it is diffracting. And the underlying principle of the experiment is to observe the diffraction effect of electron beam to study the wave nature of electrons. We want to study, actually they were doing experiment for some other thing, but this was the first experiment that proved the wave nature of electrons. So the underlying principle is to study the diffraction or observe the diffraction effects of electrons. Now what is a potential box? So in quantum mechanics, the particle in a box model, it is also known as the infinite potential well or the infinite square well. It describes a particle which is free to move in a small space but surrounded by impenetrable barriers. So always we find this term potential box when I am talking about box. So it is analogous to an electron which is trapped inside a metal. So if you are talking about an electron which is trapped inside a metal, the electron cannot come out easily. It has to be inside, but inside the metal it can freely move. It can move very freely. So we are trying to bring the analogy with the help of this potential box. So this potential box, sometimes we will call it as potential well, or we also call it an infinite square well. So what we are seeing here, you see here, this is the well we observe. and this is the particle. The particle can move inside, but it cannot penetrate and come out because the barrier, there is infinite or impenetrable barrier. The potential here is infinite. So they are impenetrable. So the electron cannot penetrate through the barrier or cross the barrier and go out. So it is free only inside this space. So we are calling this as a potential box. Now what is normalization? What is the normalization or the normalizing condition? The probability per unit length of finding the particle at position x is given by P is equal to psi star psi. So when I'm talking about a particle, the position of the particle is fixed. I can locate where the particle is. But when I talk about the wave nature of this particle, I cannot exactly locate the position of the particle. It can be anywhere, here, here, anywhere. But I can talk about the probability of finding the particle in this region. So the probability per unit length of finding the particle at a position x is given by P is equal to psi star psi. The P is the probability which is given by psi star psi. Psi is the wave function, and wave function is a complex quantity which is not measurable. So we always try to multiply it with the complex conjugate, that is psi star, so that it becomes measurable. Now psi is a function of x and t. It varies with position and also the time. So we are writing it as P. The probability is given by psi star psi. Now, if I talk about what is the probability of finding it somewhere along the x-axis. So now, if I have a particle here, this is the origin, this is the x-axis. What is the probability of finding it anywhere along the x-axis means I need to integrate it within the limits 0 and x. That is the x-axis. So I do integral of P dx is equal to psi star psi. Now when I say probability, if the particle is there, I have to find it somewhere between this region, in this region. So the total probability of finding the particle must be unity. And that is denoted by psi star psi is equal to 1. Integral of psi star psi is equal to 1. This we are calling as the normalization condition. The normalization condition is what? Integral psi star psi is equal to 1. Now what will be the velocity of matter waves? So matter wave can travel with more than the velocity of light. How is it possible? We don't know any particles that travel with velocity greater than the velocity of light. So we are trying to understand how do we say that matter waves have velocity greater than the velocity of light. So we'll take the Planck's equation, E is equal to h nu, which was given by Planck's equation. And we also take E is equal to mc square, which is the Einstein's equation. Now when we equate to, the left hand side is the same, so the right hand side has to be same. So h nu should be equal to mc square, both on the right hand side. Now if I write the formula for nu will be equal to mc square upon h. I just bring the h here. So nu is mc square upon h. Now I try to define the wave frequency, angular frequency or the wave frequency. Omega is equal to nu lambda. So for nu, we are going to substitute mc square by h because we have got nu is equal to mc square by h. Now if we cancel these terms m and m, h and h, we are left with c square upon nu. So what we are having here, omega, the angular velocity of the wave we are talking about, matter wave, is given by c square upon nu. So I write it as c into c by nu. And this velocity nu is always less than c, even if it is there. No? So if we cancel it, then omega will be greater than c, because this is small. The denominator is smaller than the numerator. So definitely c multiplied by something, we get omega greater than c, which is not practically possible. So we only say that matter waves are a symbolic representation. In practical, we cannot talk about them because we cannot have velocity greater than the velocity of light. Next, define energy spectrum. So energy spectrum refers to the possible energy of the system. Spectrum means what are the possible energies that can be there in the system. So for a bound system, the energy system is discrete. Discrete means not continuous. And for an unbound system, the energy spectrum is continuous. So that is what we need to understand about the energy spectrum. If the system has bound states, then the energy is discrete or not continuous. But in an unbound system where it is free, like we see the scattering states, the energy spectrum is continuous. Now define eigenvalues and eigenfunction. Eigenvalue is nothing but the energy of the particle. The energy of the particle, we are denoting it as eigenvalue, denoted by En. And eigenfunction is the wave function, is defined as the wave function, and it is denoted by psi. So we are discussing about the energies. Energies are nothing but the eigenvalues. We have discussed about the wave function. So the wave function is nothing but the eigenfunction. Now, what are the assumptions for the region in which the particle is in a potential box? What are the conditions we are putting in this box? So when we see here, we are considering a particle which is lying inside a box of side or length L. So this is L. And there are impenetrable barriers, or the potential at this point at the ends is infinite. Means the particle cannot cross the barrier and come out. So the particle cannot exist outside the box, and it cannot have infinite amount of energy. And the wave function is between 0 and L. So it can lie only in this region. So psi star psi, if I take only in this region, it is equal to 1. It cannot stay. If I take outside, it should be 0. It cannot stay outside. Then define principal quantum number. In quantum mechanics, principal quantum number n is assigned to each electron in an atom to describe its electron state. And its values are the natural numbers from 1, making it a discrete variable. So whenever we talk about electrons in an atom, we have the nucleus at the center and electrons revolving around the nucleus in fixed orbits like this. Okay, now when we have to assign the electron state, then we are denoting it by n is equal to 1, 2, 3 and so on. They are discrete values. Now define angular frequency. Angular frequency omega is a scalar measure of the rotation rate. Scalar means we talk only in terms of magnitude and no direction. It refers to the angular displacement per unit time. Angular frequency denotes what? Angular displacement per unit time. So if I have to write the generalized formula, omega is equal to theta, the angular displacement upon time. Now, if I talk about a particle which is making one complete revolution, it is starting from here, moving like this, and coming back to the same position in time t seconds. So what is the angle through which it is moving? One complete rotation. The angle through which it is moving will be 2 pi. And the time it takes is t seconds. Or this is called the time taken for one complete revolution is t, time period. The time taken for one complete revolution is given by capital T, the time period. So we can write omega is equal to 2 pi upon capital T. So we are using this formula. Omega is equal to 2 pi upon capital T. Next, what is the Schrodinger wave equation? It is a mathematical expression which describes the energy and position of the electron in space and time, taking into account the wave nature of the electron inside the atom. So Schrodinger equation, when we are talking about the dual nature, that particles also exhibit wave nature, then we need an equation to express its energy and position. So Schrodinger wave equation is a mathematical expression which describes the energy and position of the particle, that is the electron here in space and time. And it is given by dou square psi by dou x square plus 2m into E minus V upon h cross square psi is equal to 0. This is the famous Schrodinger time independent equation. Here we are talking about time independent equation. We also have time dependent equation where the time also varies. Now define the term quanta according to Max Planck. So Max Planck postulated that electromagnetic energy is absorbed or emitted in discrete packets or quanta. So whenever energy is emitted, it is emitted in the form of small packet. And they are discrete, they are not continuous, in small packets like. So what is the energy of each packet given by? Is given by E is equal to h nu. So this will be the energy of each photon or each quantum. Now define the term photon. A particle representing a quantum of light or other electromagnetic radiation. So we are calling it as photon. A photon carries energy proportional to the radiation frequency but has zero rest mass. That is what we have seen. Energy is proportional to frequency of the radiation, and we put a proportionality constant h which was given by Planck, and we are writing it as E is equal to h nu. So what is the energy of the photon given by? E is equal to h nu, but the rest mass of this photon is 0. So for clarity regarding these definitions, you can refer to books by P.K. Palaniswamy, Engineering Physics. You can also refer to Engineering Physics by Gaur and Gupta, or Modern Engineering Physics by Vijay Kumar and Chandralingam. Thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.